proving the existence of a solution, of a unique solution for the heat equation, and the heat equation is only a paradigm, and in the second step we will then see how to extend this proof to more general cases. And what we have seen up till now, our approach is the implicit Euler method, and what we have seen meanwhile is that from the implicit Euler method we can construct, of course there are other possibilities too, but two are obvious. We can construct two time-space functions. So we have, so to speak, via implicit Euler, we have for a sequence in time, we have functions, so elements of the Banach spaces, which we denote by UK from H1 0 of omega, which is our basic space, and from this we can construct two functions. The one we call U tilde n. N is the parameter of the discretization, so we have n plus 1 points in space. So this is piecewise constant in time. And we have also defined a name for this space, namely we call this then the Vn functions, I think. So this is element Vn. Vn meaning those functions which are, let me write it a little bit shorter. If I abbreviate this with x, is L20Tx. Let's do it like this, piecewise constant in time on this fixed discretization of time. So that is one version, and the other version is without the tilde. These are the piecewise, these are the affine linear, continuous. So if you want, these are the linear splines, the S1 splines, these are S0 splines with Banach space valued functions here, and this space we correspondingly we denote with Wn. Okay, so what is now the problem to go to the limit? So now we have seen by doing energy testing with the solution itself, we have seen estimates, namely where are we? We have seen that we have first of all, let's write down the equation. So if we want, we have now the following equation, time derivative of un, because this is just the difference quotient on each interval. That is what, in our definition of the implicit Euler, equals Laplace of un, because we always took the right on such a subinterval of the time, we took the value from the right end point. So this is then corresponds to the implicit Euler. So this is now, so to speak, our method. And the technical problem which we now have, we have here two different sequences of function. So of course we would like to go to the limit, but in a first glance it's not so clear whether the limit functions are the same which come out here. So let's see what kind of estimates what we have. What we have seen is, we have seen that the U tilde is, the U tilde n is even in L infinity. So as we have estimated this pointwise, and by this piecewise constant definition, so for every time instant, we have bound in this space here. So first for the gradient comes from the equation, and then by Poincaré for the full H10 norm. So, because of this, we have here now a bound in pointwise in time. I'm not so sure. Yeah, we will not use this L2, L infinity, we only use the L2 because we have to work within reflexive spaces and the L infinity is a problem there. So we don't use the full information. What does that mean? Because we bound here in H10, we bound the derivative, the second derivative, so to speak, one step lower as a functional. So we have here a bound in L2 0t h minus 1 of omega. Okay, so that is the situation. These are the spaces where we have the bounds. And for the function itself, and here for the derivatives which appear. So that is not that bad. That means this is again a reflexive space here. So we know boundedness means convergence, weak convergence of a subsequence. So we have this convergence here, but the question is the limit function the same? So, and for this we have a lemma which helps us to compare this. This is this lemma here, and it basically says, with all these and so on, and we do this now for general functions f. So we start with a function, do we need a continuous function? No. We only need values. So the setting is as in general. So we have these points t0 to tn. We have the time stepping, which is not necessarily equidistant. We have the delta t going to 0. We have the function values. So we have, let's say, function values. Let's call them here in a neutral case fkn, n denoting the fineness of the discretization. Function values in some x. We can do this in general. So x is here a Hilbert space. And then we have, from this, we have the fn, the piecewise, the fn element vn, and f tilde n element vn, and the f n element wn. So on the one hand side, we do piecewise constant interpolation, and here we do piecewise linear interpolation. And the question is, how are these limits, if they exist, related to each other? And the answer is they are the same, independently from which side we start. Here's one formulation, namely, if for some then limit g from LP 0 tx, we know that the Fn, the piecewise linears, converge to this function g in the LP 0 tx. Then we also have the convergence of the piecewise constants to the same limit. And actually, we have also the result vice versa. So we can also start with this limit and conclude that we have this limit. And this resolves then the problem here. Because, okay, we will see how it's resolved then here. Yeah. Function value in a general setting. Of course, these are elements of the Banach of the. So this is, so to speak, the everything which contains the spatial information. These are actually as functions in space, these abstract points, and we interpolate them in time, piecewise constant, piecewise linear.
Okay, so the function value more or less is about time.
It's for this function here. It's for this function which we are going to construct. Okay, I'm not going to all the details of the proof. The important thing is that we can estimate. So what the difference between these two function constructions are not so strong. And the only thing is we have to see how these norms relate to each other. And maybe go to this blackboard. The important thing is basically to show the equivalency of these norms. To show that it's possible to estimate one norm by a constant times the other, where this constant, of course, is not allowed to depend on the n. Okay, so let's start with this Fn norm. Let's call it equivalency of norms. Let's start with Fn in the L2 0Tx norm. So what does that mean? Okay, so what do? We integrate in time. We break up this integral in time in the integral over the what is our over the subintervals. So we have here a sum over the subintervals. Each subinterval has the length hk. We could also take it equidistant, doesn't make too much difference. So the integral is now here. So actually the integral is from now tk, to think, tk to tk plus 1. And now we do here a transformation in time, such that we have here the integral 0t. And now we are on the unit interval, and what we do there is we just integrate in time. We just interpolate linearly between the two values fkn and the value fk plus 1n. That is, we get here a t, and we get here a 1 minus t. So that is, and what is the integrand? The integrand is, so what are we doing? So we're doing the L2 norm. So we have here the norm of x of this thing squared. And that is now not the norm, what we have here, but the square of the norm. So that's just the definition with this light transformation. So, and you see now it becomes a little bit nonlinear, but this is really controllable. So we can rewrite this here as we just multiply this out, what we have here. So we get here again something like, so what do we get? This term is t squared, and the first value, the first norm squared, I'll now leave the x away. Then we get the other term with the 1 minus t squared. And then we get the mixed term. And the mixed term is here just 2 times this, integral t 1 minus t, and here the scalar product fkn, fk plus 1n. Okay, here. So, okay, you see, the integrals to be computed are not too hard. There are these functions which we have to integrate. That's the only variable in time thing which comes up. So we do this, so we get a 1/3 from here, we get a 1/3 from here, and from this term we get correspondingly also a 1/3. So that means we have now the following situation. We have here this factor 1/3, which of course is of no harm. And then we have the constant terms with the two squares and the scalar product here. And now we do this, what we have discussed already several times. We have such a mixed term, and we separate this mixed term to absorb it with an appropriate inequality sign, to absorb it into the into the non-mixed terms. Of course, the modulus of this is just Cauchy-Schwarz. We can estimate by the square of the norm by the norm times the norm, and this again a times b we can estimate, and this is the separation then just by binomi 1/2 norm squared plus 1/2 norm squared. So these things appear with a minus sign. Okay, we want to estimate in downwards, so we have to let it appear here with a minus sign, and then we have a 1/2 going away from. So basically, this is greater or equal than 1/2 minus 1/2, and here the norm squared. This is these two combinations of estimates which I just reminded, and so one we get here 1/2 away, and so this goes down to hk over 6, and then we have here these things here. And now you see we are basically done, because it is even quite simple here, because we want to estimate from below, so we can throw away positive terms which we don't need. For example, I think we take the right-hand value, so we take this value, so we throw away this value, and what we get out is something like 1/6 sum over the hk, the squares, and this is just the integral of the piecewise constant thing squared. Okay, so this is one estimate, and you see that actually we can also reverse the argument here, modify the argument here, and also get the estimate in the other direction with another constant. So actually these two norms are equivalent, and because of the equivalency, we can now argue that is something we have to take for granted here. We're not going to prove, is the following, namely that we can, in general, we can we use that those if we have a function, so this was here the situation was we have had those values, let's say. There's no function necessarily behind. And then we have the interpolation. If these values which we interpolate come from a function, that is, if we have a function g from L2 0 tx, and these values have to formulate it a little bit differently. Or is there a problem? Okay. Yeah, okay. Now I'm missing one step. So if this would be a continuous function here, if we would have a c here, then of course we could say, okay, we take those values at these time instances and we interpolate them. It's just as with linear piecewise constant interpolation. The only thing is here this technical point with the x-valuedness, which we try to keep our hands on, but the principal reasoning is the same. But now, and then we would have those values, and we could look at the interpolating functions, either piecewise constant or piecewise linear. This we cannot do with an L2 function, but because we cannot evaluate this at a point. But what we can do is we can give us, so to speak, averaged values. So we can define something like averages over the interval so 1 over hk, and now we interpolate those averaged values. There's a problem because we have no value at k equals at the index 0, so we still need a definition for G0n. As we're only looking for L2 convergence, it doesn't really play a role which value we take. It would be different if we would aim at L infinity convergence. But let's say we just take the same value as the neighboring value to make it well defined. So, and then what we're now going to use is, then we have the interpolants. And so the gn function and the gn tilde function. And what we now try to use, what we do not, what we now will use, what we will not prove, is the following: that those interpolants converges to G in L2 0 Tx, and correspondingly the piecewise constant version. So one has to work a little bit with the fact that we have here average values and not values, but then this is not so much more than just saying the piecewise constant interpolation is converging in L2 and the piecewise linear interpolation is converging in L2. We're not claiming any rates or whatsoever. So these proofs can be done just as it is done in numerics. You prove this, and basically the only thing yeah. It is a direct estimate, so I'm going to skip that. On the basis now of this intermediate fact, now the argument is as follows. The first thing is the Fn, so this is now the sequence from here. We compare the Fn with the Gn. The Gn is now the interpolating sequence to the limit G we have here. The Fn and the Gn, if we compare this, we can compare this by getting something in between. The G, that's now an elementary estimate. And now we have both of these. So this goes to 0 by assumption. This goes to 0 by this remark. So here we have convergence for n to infinity. So that is the one thing. Now we compare the Fn tilde with the Gn. And with the Gn tilde. So. But this is up to a constant, as we have seen here, up to a constant. The constant is 6, by the way, but this really doesn't matter. Up to a constant, this can be estimated by the corresponding differences the piecewise linear differences can be estimated by the piecewise constant differences can be estimated by the piecewise linear differences, and there are, as we have seen, they go to 0. So, and now the last line is sufficient to conclude the proof. Namely, now we would like to see what about this quantity here. And yeah, it's clear. We do now these auxiliary functions in between. It's quite a simple reasoning. And okay, this quantity goes to 0, as we have seen. This quantity goes to 0, that is this statement. So we have convergence. So, okay. So how can we now proceed here in the argument? Seite 13. So, okay, what is now the situation? We know we have, for example, this boundedness. That means u tilde n converges to some u tilde weakly. I now always omit noting that it's a subsequence, actually, that we're always selecting subsequences. Weakly is I denote with this half arrow here, weakly in this norm. On the other hand, we have for the un, yeah, so on the other hand, we look at and because of, yeah, why is this? I don't know, anyway. I'm a little bit confused here with the tilde and not tilde. Okay, I think this is okay, but maybe not enough. So what is claimed here, what is the argument here? We have the boundedness of un in L2 0T H1 0. In principle, we can always refer to this estimate here. This estimate and the reverse estimate tells us it really doesn't matter whether we take piecewise constant or piecewise linear interpolation. And for the value, certainly we have that. And what we also have seen is that the time derivatives, that is the difference quotients, that the piecewise constant functions consisting of the difference quotients is also bounded, but now only in h minus 1. So now we argue with the compactness result. So what do we have here? We have boundedness. So we are here bounded in a space which has the function in an L2 space with some x, and the derivative in an L2 space with here the x prime. And one of the compactness result was that because of this boundedness, including the time derivative, we can conclude that we have, and that is now of importance, that we have a strong, not only maybe this was a red herring, we get now not only weak convergence, of course we could get weak convergence here, we would get weak convergence here. We get now strong convergence if we go, so to speak, in the intermediate space of the Gelfand triple, namely the L2. So this all together tells us that UN is strongly convergent to some U from L2 0T L2. That was one of the compactness results. Okay, so now our auxiliary consideration tells us that also the other version, the piecewise constant version, does the same type of convergence with the same limit. So that is the status we have. And now because of this convergence here, we also have convergence of the distributional derivatives. But we look at the time derivative as a distributional derivative and the Laplacian as a distributional derivative. So we have the same type of convergence. So, but as we have here equality in the distributional sense, where was it? We have not written it. Yeah, we have here equality for all those function elements, sequence elements. Then we also have it in the limit. So the first consequence is for this limit function here, we have the heat equation in the distributional sense. And of course, we preserve those regularities as we had it, because all these are Banach spaces, or even not necessary. So for the limit, we know exactly this regularity which is stated here, So we can summarize this. The only thing which is now still missing is are two things. The one thing maybe I'm not going to work out in detail is the validity of this energy identity with which we get from testing with the function itself. So we have let's maybe summarize. We have the U fulfills distributionally the heat equation. And so this we have seen, and this we don't work out in detail. We also have what we would get by doing formally, or what we've started off with, this formal testing saying that the piecewise almost everywhere in time. Yeah, okay, maybe I have to have an intermediate thought. So what does that mean? Because of this situation now, that's another embedding theorem which we need. The situation that we now have, maybe I put it first in between. So what do we now know? We know now that the U is in L2, 0T H1 omega, and the time derivative of U is L2, 0T H minus 1. And one of the other embedding theorems tells us that the function is now, if we so to speak relax here, if we go now to LP, the function is even a continuous function in time. So this is quite important to talk about the initial data. Without having this continuity, we would be forced to talk about the initial data also in a weak sense, in a trace sense. Now, having a continuous function in time, there's an immediate meaning what u at t equals 0 has to be. It always means, of course, there's a continuous representative in this L2 function class, and so on. So that is the one thing, and what also holds true, which I will give an argument for that, but we can basically, it's just one writes down again the equation with the capital N and then goes to the limit, and then we get, and that does now make sense that we write this down, because we can evaluate now at every instant of time, but only having L2 here, not H1. So we get this identity. So the energy, if we denote this as the energy, is the initial energy up to this dissipation term. So, but mathematically, as I said, the notion of energy in mathematical analysis of PDEs is a little bit, is very, very generous notion in terms of, let's say, thermodynamics. So basically everything is an energy. We get this just by testing with the function itself, which we could not do, which we could only do formally, but via this version with the n's here, we can now derive this as a limit. So, and the initial data, so because of the strong convergence, because of the, and this embedding is also continuous here from these spaces here, so we also have convergence in this space. So because our approximate functions also fulfill the initial data, also our limit function fulfills the initial data. Let's make it as short. I think there's not so much to say about that. And now we can summarize everything in a theorem, and then we are done. Not really done, but okay. Let's summarize this in the theorem. This is the existence theorem, so let's now state everything again. So we have our bounded domain in omega, not very much regularity required, only what is necessary to have those Sobolev spaces. And now there's a difference now in the existence result. Namely, up till now, our initial data had to be an H1 function, which is, in the light of this estimate, is not very natural, because here only L2 appears. And we know also from the classical solutions that we have this enormous smoothing in the heat equation, that we can solve, of course, the heat equation also for functions which have not only kinks as an H1 function, but also jumps initially. These jumps will vanish immediately. That tells us the classical theory, and that should be reflected here. So what we actually want to have is here we want to have L2 function, which we have not yet in the program. So this is now new in this theorem. And the statement is then there is a solution U in L2 0t H1 0 of omega. So we are still talking about the homogeneous heat equations with homogeneous Dirichlet condition. That is, we are talking about the equation time derivative of u minus Laplacian of u equals 0 in space-time plus, maybe I added u equals 0 on delta omega, that is included here, and we have our initial data at 0 with the function u0. The statement is, let's call this the first equation, this then the second, and this the third. So the first equation holds distributionally. Again, what does that mean? Holds distributionally. That means that the derivatives which we have here not necessarily exist as functions. They only exist as functionals. So we have to multiply with a test function and put the derivative on the test function. Then it makes sense. We have, for example, looking at the space derivatives, of course we have the first derivatives we have as function, only as L2 functions, but we have them as functions. But the second derivatives we don't have in general. And the same applies for the time derivative. And that makes a little bit of a problem, because as the time derivative is, and that is how we circumvented this problem, as the time derivative is not a function, we can also not test with the time derivative. Okay, how it's distributionally. U is a continuous function when one can make this more complicated, but I'm not going to do this. U is a continuous function in time, and 2 holds, and 2 is included, of course, in the formulation, and 3 holds. Yeah, that's it. As we have a continuous function. The full statement would be the initial data hold in a trace setting, and for the continuous representative, it holds in the classical sense. But okay, this is maybe not so. And give this a number here. This is 1113. And 1113 holds. So that is the status which we have. So what is missing in this proof? I told it already. So if U0 would be in the H1 0 of omega, everything is okay. This we have proven. So, and now again, meanwhile, it should be clear how we do this. We go, this is an infinite sequence. We go level by again approximating the old situation by the new situation. The new situation by the old situation. So what we do here is an approximation. Maybe I skip the details. Approximation of general initial data. That is, what we are doing is we have our U0 from L2 of omega and approximate this by some sequence U0m from H1 of omega, H10 of omega, and this is just by the density of this function space in this here, that is in the L2 sense. And now, and I guess I skipped this, the reasoning which is now necessary. So what we now are going to do is we look at the solutions which belong to these initial data. These we have. And then we have to see that we can go to the limit there and get a solution with this general initial data. But the bounds are independent, the bounds can be made independent of this approximating sequence. So all our bounds which we have seen are uniformly here. So we can see all this convergence which we have seen before also, and we can repeat all the reasoning, and yeah, basically that's it. Maybe we skip those details. So the question now is, The question now is, was it worthwhile to do all this effort? Because up till now we have just dealt with quite a simple equation. But what I try to convince you now is that all what we did now can be very much generalized up to general parabolic, so to speak, the most general version of parabolic equations. Linear parabolic equations first. Nonlinear, of course, is another question. Okay, so let's have a look at that. So the first step is, that's not very difficult, is a right-hand side. We call it f. So what we would like to have, we would like to have the equation time derivative of u minus Laplacian of u not equals to 0, but equals to f. So let's see what kind of assumptions we need for this f. And as we have seen, the most weakest version in which this makes sense here is that the left-hand side is in L2 0t h minus 1 of omega. Also this right-hand side has to be there. So that means we can deal with right-hand sides which are not functions but also functionals. This gives us, so this is already quite a step beyond classical theory. So we could have something like very concentrated sources which are no functions anymore in the equation. We could model this. Of course, we can allow here any L2 in time and space function also, but we can allow here for more. So, if we now repeat our procedure, then I abbreviate it a little bit. If we do the a priori estimates revisited. Let's first do it formally. Formally, as we started, on the continuous level. So what we always did, we test with ut, and that means we get here the terms which are good, and in additionally, does that mean we get a term of the type time derivative, integral over f of t, this is the right hand side, and we let's call it s, and we test with u, so we have this additional term here. So, but this term is of no problem whatsoever, because what do we do with this term? We just what we do here, we can separate here, we can use Cauchy-Schwarz here, so we get the product of the norms. And then finally, we can separate this term, not necessarily with the same weights, 1 and 1. We discussed this already, but we can give one term a high weight and one term an arbitrarily low weight. And we will give the arbitrarily low weight to this term here. So we can estimate this by something which we call delta. And what is then left here? Maybe I write it down first. And then we have here the u. It's even, let's see. Okay, so we do not do this. Maybe I have to correct myself. That would be one version, but we want to do it another way. we do not view this as the L2 scalar product, but we view this as the duality pairing between the H1 and the H minus 1. We cannot, for doing it in L2, we need an L2 property here, which we want to avoid. And therefore, we get here the H1 norm. And here we get something constant over, I can also make it in this way, I think. 1 over delta. And here we get then correspondingly the H minus 1 norm. Because we only have the H minus 1 norm, then we have to take the H1 norm, but this is okay here. So what do we do with this term here? And that is the reason why we made this delta small. This we absorb, that is the wizard's word for that. This we absorb in the left-hand side. In the side we would like to estimate. Because there we have this term already. And now if we make this delta smaller than the constant which appears in front of that, we do no harm. We only reduce a little bit this constant. And here we get then correspondingly something to the right-hand side. So we get, at the end of the day, we get the same a priori estimate as we had before with this term here on the right-hand side. So we get something like ut or for every instance of time, it's maybe better to write it like that, plus the integral of the gradient. That is the term which was enough to absorb this term here, because this term, so to speak, fully represents the H1 norm via Poincaré. And in this full Poincaré norm, which we saw, a full H1 norm which we have absorbed this term here. So we have this thing here. Maybe write it a little bit different here. And then we have here a constant, and here we have the initial data. This is in L2 here. This is all L2, what is if it's not noted, but anyway. Then we have the initial data squared, and then we have here already the f in the squared in the L2 h minus 1, exactly in the norm which we would allow. So, and that shows basically that everything goes through. Now, this is the continuous level. If we now go to the discrete level with the Euler approach, then of course, if the f would be independent in time, then it would be very simple. Or it would be continuous. If it would be independent in time, or it would be continuous in time, it would be very simple. Then we do it as we would do it numerically. We just evaluate the right-hand side in the Euler equation, in the Euler approach, also at this new time level. But now we only have an L2 function, and therefore it's now clear what we have to do. If we look at the reasoning which we did here, we have again to take averages in time. So the implicit Euler now has to read here as uk plus 1 minus uk over delta t equals uk plus 1, and now plus the right-hand side, some fk plus 1, but because of lack of continuity in time, the fk plus 1 has to be defined now as the average over the corresponding time integral of the f. So again, we have to deal here with such a piecewise function composed out of averages. And that this all works, and I'm not going now to go into the details, that this all works finally has to do that again, if we now do that, so we have now these values, and these fk's again give rise to a function f tilde of n. So this is now again the piecewise constant interpolant of those averaged values, exactly as we did it in the other situation. And what is important to note, I'm not going to do the proof because the proof is really, again, very simple norm estimate. If we now look at this function here, in some L2 function, independent which image domain X we have, we can estimate the norm of this piecewise constant function by the original function. So there's no... That means if then something like this comes up naturally in the estimate, we can always estimate it by the original function. So I think that should be enough to fill in the other details for the right-hand side. Next step would be to clean the blackboard. It's not formulated as a theorem, but basically it says the theorem would say what we have seen till now also holds true with the right-hand side, f from this space, L2 0 t h minus 1. So next step would be inhomogeneous boundary conditions. Okay, so what we are equations? It would be something like that. And now that is clear what that means, meanwhile. And now instead of u equal to 0, we would like to have u equals to g. And this is now on st on the lateral boundary of the space-time cylinder. And of course, we also have our initial data furthermore. So what is this supposed to mean? We discussed, if you have seen the same discussion already for elliptic problem, then you know what one has to do. As we have h1 functions, let's first discuss this elliptic situation. If we have h1 functions which are not continuous, so we need the notion of trace. We need a continuation of the evaluation operator at the boundary. And we need the continuity of this operator, which tells us that it's a continuous operator from h1 to, let's say, L2 at the boundary with the corresponding n-1 dimensional measure. But this is not a surjective function, that's only a subset of the L2, which appears as images of traces of H1 functions. And this subset, this new space, we call then H1 half also. So H1 half is only a notion for saying it's in the image of the trace operator. Or in another notion to say not every L2 function is in the image of the trace operator. So if we would start with this function g on the boundary, it's not enough to say it's an L2 function in time. Because then it's not even, because any notion which we have here needs to say, forget totally the first equation, it's in the trace. So the minimum assumption is sort of being in this, in the image of the trace. Is this notion being in the image of the trace, and if we are at that level, then we can equally well say, okay, we say G is a function, is just any extension of the data to an corresponding H1 function. That's the way one can deal with that. So if then we subtract this function, then we come to a problem with homogeneous data and so on. And that's the same thing what we can do here too. So let's say G is an extension to let's do it in space and time, meaning that the trace for almost every instance in time, the trace of G of this extended function, the trace in space is the function we would like to have. So this function G necessarily has now to be, such that all this works well with the traces, has to be an L2, that is what hopefully is enough, L2 in time, and in space we need H1 of omega. So the equivalence statement would be that the trace, that the function at the boundary is in something like L2 H1 half at delta omega. So, but this is not enough, because what we would like to do is now, what is the approach? The approach is now, what is the Ansatz? The Ansatz is now that we say, as in the elliptic case, that we write our function u now as a function g plus v. And because all the boundary data are already in the g, the v now can have homogeneous data. So v is then supposed a function from L2 H1 0. So what does that mean? What kind of equation now does this v has to fulfill? We do it formally, and we just put our operator on the whole thing. So we have f equals time derivative of u minus Laplacian of u equals time derivative of, let's start with that, g minus Laplacian of g, and the same thing. That's now just a formal reasoning. We have this thing. So we would like to transfer the problem from a problem for u to a problem to v, because they have now those homogeneous data which we know how to handle. What does that mean for the equation? That is stated now here. We get again now the heat equation that would work with every linear operator for this function v with a modified right-hand side. So this thing has to go over here, defining some f tilde. And of course we have to have the right meaning for that. So this is not a u, this is a g. What is this here? By assumption, this is an L2 h minus 1 function, so this is okay. This is allowed, and now you see that it was not just a nice addition that we could allow for these very rough right-hand sides. It's really necessary here to deal in this way with the boundary data. So this whole thing here is in L2. Yeah, let's first say this thing is in L2 0t h minus 1. So this is okay. Going to the other side, modifying the f, and then we have our new problem. But this thing must fulfill also the same condition. So therefore, necessarily, at least for this approach, necessarily, we need also some basic regularity. It's really basic, as it's only in distributional, not a function, for the time derivative of g. So that is what the data have to fulfill I'm not going to claim that it's absolutely necessary to show the existence of the solution or give the solution a proper notion. But at least for this approach. But now I think if we are at that level, now basically the situation is clear. So what we have done is we have transformed the original problem for the U with the inhomogeneous data to a new problem for the V with homogeneous data, but only with a modified right-hand side, but the right-hand side is in the class which we can handle. That's it. Of course, we could also repeat all our reasoning we did before. We could also do alternatively again implicit Euler, and we have to deal then with the inhomogeneous boundary data, then again with averages and so on. That would be another possibility. Okay, so next step is other boundary conditions. And before we come to the general boundary conditions and the general operator, we go to the situation which for the stationary problem, for the elliptic problem, is the most critical one, namely the situation of pure Neumann boundary data. So what we have here now is we have, okay, let's do it again. We have our equation. And now our initial data, of course. Oops. And we substitute now the statement, the values are prescribed at the boundary, which for something like temperatures or masses is something pretty critical to perceive what that means in an experimental situation. How do I tell my point at the wall that it should be at 5 degrees? It's not so clear to me. I have some idea how one can do that, but that would really mean having other boundary conditions which approximate the Dirichlet boundary conditions. But what is a very natural boundary condition is the Neumann boundary condition, which here just means, I write it here in this notation, nu. Nu is the outer unit normal. For some reason, Schweitzer has the unit, the normal first. Looks a little bit strange, but anyway. So we prescribe the gradient in the normal direction. We prescribe the directional derivative in the normal direction by some function which has here, okay, I promise to use the notation of Schweitzer also. It's really difficult for me to do that here at that place. It's impossible to call this psi, but anyway, we do it. Okay, so what is the problem in the stationary case? The problem is that no derivative, that the function itself does not appear, and therefore there is no uniqueness in this problem. For every solution we can add a constant and we get a new solution. Actually, that's the only variation which is possible. Therefore, a direct application of Lax-Milgram is not possible, but we could very slightly modify the situation and then also apply Lax-Milgram. For example, going to a corresponding equivalency relation which puts the functions together, which only distinguish with a constant. So, but on the direct level, we see we just don't have coercivity of the operator. And then, if we would like to save coercivity, then you possibly heard this discussion already. Then one can do various modifications in the equation. One modification would be not to have a pure Neumann condition, but a mixed boundary condition. That is here with additional term function times u. That would be something like Newton's law of cooling, saying that the flux, that is what is prescribed here, that the flux is, say, proportional to the difference between, let's say, the temperature inside and some ambient temperature, or whatever we model. And then we would get here a term in which will help us. Maybe we write down the weak formulation. If we write down here the weak formulation, so what would we get? We would have here something like, this also takes into account that we will not have the time derivative as a function, so we put it over to a test function, which is called here phi. And then we get here, and that is why these Neumann boundary conditions, also called homogeneous boundary, natural boundary condition. If we now do the standard procedure, multiply with a test function to partial integration, then just nothing appears. No boundary term appears, because the boundary term which, no, this is not true, that would be in the homogeneous case, but now the following term appears. It's, I put it to the other side, it's psi. It's the normal component. It's the psi times the test function phi. So natural, because now the boundary condition is incorporated in the formulation. We don't need to impose it on the functions we are dealing with, as we do it with the Dirichlet boundary conditions. So that comes from the partial integration here, and then of course we have the right-hand side just multiplied with this test function, and then by the partial integration we sorry, I have to put it on the other side. So we just this here, f times the test function, and then by the partial integration from here we still get a term which involves the initial data. Yeah, and what does that mean for the test functions? The test functions, they should allow partial integration in time. So we have h1 in time. We have values in h1 of omega. So no imposement of boundary conditions here anymore. And of course, as we did this partial integration and only the lower value appeared, we need something like, for the test function phi at t is 0 as a trace. So that would be a weak formulation incorporating naturally the data, the boundary data. But this only gives, this is only a part of the right-hand side. If we now look at the operator, this is just the old operator we had before. Nothing has changed. The only thing is that the space is now larger. That is, we cannot rely on Poincaré anymore. So that's the only difference we have to deal with. And actually, there's no problem with that. And let's first discuss how it would be, how we would deal with the situation in the elliptic case. So here we would now have an operator which is not coercive on the full H1. So how could we help ourselves? One way, as I already started to discuss, would say we don't have Neumann boundary conditions, we have mixed boundary conditions. We have an additional term, alpha times u here, with a positive alpha. That would mean that an additional boundary integral would appear here, something like integral over the boundary in the L2 of the functions itself, function times test function. And then we would need something, a variant of Poincaré, which is also called Friedrich's inequality, which tells us if we have this additional term is sufficient to control the full H1 norm. That would be one way. A much, much simpler way would be if we would have another operator here, if we would not have minus Laplace of u, but minus Laplace of u plus a positive constant or a positive function times u. Something like a reaction term which works as a which acts as a source. Which works as a sink for the quantity, because the factor should be non-negative, should be positive. What would that mean? That would mean that we would get here an additional term, positive function d, let's say, times u times phi in the integral. Yeah, and that's enough. Then we have the full H1 norm. That's a very simple way to get the full H1 norm. Okay, why I'm telling that? Because now I really have to deviate a little bit from the reasoning of Schweitzer. Schweitzer is a very good book, but from time to time he has the tendency to make the things more complicated as it really is necessary. He says, okay, one should then work with averages and subtract averages to restore the Poincaré inequality. But what we have to do now, I think, we only have to look at the Euler equation, at the implicit Euler. Let's just remind what the implicit Euler was. Do we have it somewhere still at the blackboard? Yeah, we still have it here at the blackboard. Don't have to write it down. Okay, here the implicit Euler. What kind of a problem is this for the new level, the value at the new level? This is just, let's write it in this way, delta uk plus 1. So this is not sufficient, as we have said. But we also have this term, plus 1 over delta t times uk plus 1 equals some right-hand side. This is now fk plus 1 plus 1 over k uk. So that means the term which I just said we would like to have is here in the approximation. We don't have here the Laplace, minus Laplacian. We have minus Laplacian plus a constant times the function. And that means there's no problem of unique existence even in the full Dirichlet case, and that means everything goes through. And so we only have to need implicit Euler as an elliptic boundary value problem for minus Laplacian of u plus constant times u, and that is uniquely solvable. What is the physical background of this discrepancy? Why don't we have unique solution in the Dirichlet case? We discussed this already at other occasions. Dirichlet boundary conditions basically means an open system. We have no control over the fluxes which act at the boundary whatsoever. So that means if we view the elliptic problem as a long time limit of the parabolic problem, we don't know what has happened to the initial data from which initially this came from. So we lose this information. In the elliptic problem, the initial data information, that the total mass which comes from the initial data, is preserved, and therefore we have here then the unique solution. Okay, so final step. I think we can do this still today. Final step now is to go to general operators. Wo ist das denn jetzt? 17, 18. Upsala, wo ist die Seite geblieben? Ach, da. Okay. Okay, so final step would be general. Again, we can do this in two sub-levels. The first sub-level would be we go from delta u minus Laplacian to delta u plus L of u equals f. Let's first start with, let's say, Dirichlet boundary conditions. And what is the L? The L is here supposed to be the following operator. We have here, instead of the Laplacian, we have minus the divergence of A times gradient of U. A is a matrix value, the tensor valued function, which is uniformly positive definite. And then we allow for a term in the first derivatives, a linear term in the first derivatives, which models forced convection. So that B would be an underlying flow field. It's a little bit different than with my notation. My notation here would this be a C anyway, and now the reaction term here is my notation. This would be a D, but I think that's not such a big problem here. And if we deal with this type of operator on the elliptic level, and again aiming proving the coercivity, then to apply a Lax-Milgram, first with homogeneous, then with inhomogeneous Dirichlet boundary conditions in the way we have discussed here. To deal with inhomogeneous boundary conditions, one comes to an assumption for the data, which we also have to apply here. So the assumptions are, as I said, the A is uniformly positive definite. And for the B and the C, there should be some regularity, which I'm not working out now. And the further assumption is that C minus 1/2 the divergence of B should be greater or equal to 0. That means, in particular, if we have a divergence-free flow field, it just means what we can handle here, at least in this reasoning, is to have sink terms, not source terms. That does not mean that the other situations are possible to show coercivity, but then one has to weight the situations. Then one has that condition comes out if one would like to handle so to speak, the influence of the different terms on the coercivity separately. Of course, one could also say, yeah, this gives us so much coercivity that this term, the other terms, could take away a little bit of it. So that would, of course, allow us, for example, forget about the B, that would allow us also to be a negative C, as long as the positive constant which comes from here is larger than what is taken away from here. But this would numerically interrelate the properties of the function. That's, of course, also possible. But if one wants to avoid this, this is a sort of a natural condition. In any case, we need just something which makes the elliptic problem coercive. Maybe write it so, or any assumption. Yeah, okay. And then maybe it's not necessary to dwell too much on that furthermore. Then one has to see how, okay, the approach is again the same, and how do these a priori estimates repeat, and the only thing is how to work now with this operator, testing it with u. Maybe I can say it with words. If we test here with u, the first term doesn't make any harm, that's just the assumption of the positive definiteness. So again, this first term gives us a control of the square of the gradient, because we have assumed that it gives us this to us. This term is also good as long as the c is non-negative, because this gives a control of the u square. And if not, okay, something else must take care of that, and that can come from this part here. If we test here with the u, then we can do a partial integration, which actually leads to this condition here, say that these two terms make no harm in this estimate. They do not give us anything, but with this assumption, but they don't give us any harm. So that means we can basically repeat everything. And finally, what would be 5 would be then the same thing with general boundary conditions, and that is the same as in the elliptic case. That means we can substitute, maybe as a first step, we can substitute the Dirichlet data by Neumann data or by mixed data, or we can also combine all the 3 types of data. Okay, so I hope this has given a little bit of an overview how we can deal with linear parabolic equations. So maybe we add a little bit next time with parabolic equations, and then the next step would be to do a similar program for hyperbolic equations, that is for the wave equations. But now we are doing it vice versa. We don't discretize in time and look at the problem continuously in space. Now we will then discretize in space and look at the emerging ODEs as an approximation. Okay.